First example, we have Carol bench pressing 85 kilograms, which is approximately 800 newtons. We'll just use the approximate weight of that for now. Each rep requires her to lift the bar about 1 meter. So the distance from her chest to the top of the rep is 1 meter in total. Now, since she's pushing the bar up with a force of 800 newtons in order to lift the bar, and since the distance is also up, that's a positive amount of work. The force and the distance are both parallel to each other, so we can figure out how much potential energy is gained during that process. So remember, the work she does goes into changing its potential energy, which is always EP final minus EP initial. Now, we're assuming chest level was 0 potential energy. That's as low as that weight can go. And the final energy would just be mg times h final. Now, mg is the force of gravity, which we're giving as approximately 800 newtons. So this is 800 newtons times 1 meter. She's giving the barbell 800 joules of energy every rep. The next question, Val pulls back a bearing in her new slingshot. She pulls back the slingshot about 30 centimeters. So the distance pulling back is 30 centimeters. And in that same direction, an average force of 100 newtons is applied. So we know that work is force average times distance, as long as those two things are parallel, which they are. So we go 100 newtons is our average force, multiplied by, it's got to be meters, so 0.30 meters. And we end up getting 30 joules of work is done. But remember, work goes into changing the energy of that object. So when she does that work, what she's doing is she's storing the energy in the slingshot rubber bands. So it's a type of potential energy. So initially the rubber bands were unstretched. So my initial potential energy is 0. So 30 joules goes into my final potential energy of the rubber bands in the slingshot itself. Now the last one, we've got a pendulum that weighs, its force of gravity is ½ Newton, and it's swinging freely back and forth, like that, back and forth. At the very top of its swing, it is 0.12 meters or 12 centimeters above its lowest position. So its lowest position is down here, string hangs straight, and at the very top of its path, from here to here, is 12 centimeters. Now, when we do potential energy, we want to know the difference between the potential energy. So we're going EP final minus EP initial. And we know that change in energy is work. So essentially, we're finding the work done to get that pendulum up to position. So it's mgh final minus mgh initial. And since the pendulum can only go as low as we see in this question here, we're assuming the initial height is 0. That's as far down as it can go. All the heights are taken from there. So we end up getting mgh final is that increase in potential energy. Now, once again, mg is a force of gravity, and they give that to us as 0.5 newtons. So this is 0.5 newtons times 0.12 meters. The force and the distance are both are both parallel to each other. And that creates 0.06 joules of potential energy. So the difference in potential energy between the final position and the initial is an increase of 0.06 joules of potential energy.